Assalamu alaikum and a very good morning to all of you who are virtually present here. I, Nashra Javed, Organizing Secretary, extend my thanks for joining us in the 3-day long International E-Symposium on Recent Advancements in Information and Communications Technology, organized by the Department of Computer Application, Integral University, Lucknow. We are associated in this symposium with the Indian Society for Technical Education, Institute of Engineers India, and it is technically co-sponsored by IEEE Uttar Pradesh section. I would like to thank our participants who have actively participated in all the sessions with full enthusiasm from last 2 days. We expect the same level of excitement for our final day of symposium. Today, we are having two back-to-back technical sessions, and there is a unique thing about them that the fact the both keynote speakers are a distinguished alumni. It's a privilege for me to invite Dr. Alam Nawaz from Yangnam University, Republic of South Korea. So, has done his PhD in chemical engineering first grade at Yangnam University and Masters of Computer Application from Integral University. He is currently focusing on the auto farming to assist farmers with advanced embedded technologies and has undertaken many international projects for the betterment of our society. So, is having varied research publications in journals of repute. Dr. Alam sir will deliver a technical session on computer vision and image processing with blockchain technology. Over to you, sir.
Okay, thanks a lot for your generous short introduction about me. Uh, let's start my screen. So, a very good morning, all of you. I am Alam Nawaz, working as a postdoc in the Yangnam University, South Korea. Today, I am gonna talk about on topic smart human machine interface for the Anamox wastewater treatment plant, which is basically a recent project of Tucson Heavy Industrial Limited Company. In this topic, I will present the challenges which I faced during the experimental and developing that software and their solution with the GUI. So let's start. So these are my contents which covers the today talk. So firstly, I will present short background introduction about the Anamox, what is it and why we are using in this project and what's the importance and benefits of this Anamox. So which is widely, actually it is widely famous recently days due to have many advantage. In addition, I will talk about the whole architecture which I proposed to the company and their workings. So before starting the talk, I would like to brief introduction about my lab. We are PSTCs, which stand for Process System and Design Control Laboratory, and mainly works on process simulation based on the LNG, liquefied natural gas, and then their optimization in terms of energy consumption. For more detail, you can visit this website. Let's begin with Anamox process overview. So here, there are two widely used treatment processes in the wastewater treatment plant. The one is side stream treatment and another is mainstream treatment plant. In this project, we had treated the municipal wastewater in a side stream biologically to remove the toxic nitrogen. Since the organic compound containing carbon but also nutrient such as nitrogen and phosphorus, which cause eutrophication of receiving water bodies and micropollutants such as heavy metals, pharmaceutical and other toxic compounds which are of increasing concern as a risk towards human health and the natural ecosystem. Basically, in the municipal wastewater, there is less chance of phosphorus, so focused on the left hierarchy, which is biological nitrogen removal, where we divided the term as mentioned in the red 1.0, 2.0, and 3.0 for getting the better idea easily. It is very important to select a right method like 1.0 present nitrification denitrification process where three or many other methods are there, but we choose in the first method because the RAS stand for the return activated sludge is intended to prevent the loss of microorganisms through the aeration tank and to maintain an adequate population for the treatment of wastewater. Whereas prevent overcrowding of microorganisms in the aeration tank, a portion of the sludge equivalent to microbial growth or yield is extracted from the system as a waste activated sludge. In the 2.0, similarly in 2.0, we choose in the SVR tank, which is sequentially batch reactor, and it's based on the processing time. And third one is categorized as deammonification, which is the just suspended growth SVR. So in this slide, in the conventional nitrification denitrification process, which is 1.0, so the nitrification is an autotropic process. Here, process is conducted in two steps. One is this part and one is this part. First, ammonium is converted into nitrite over hydroxylamine by ammonium oxidizing bacteria, where oxidation is used to convert ammonium to nitrite. Approximately 1.5 mole of oxygen as electron acceptor per mole ammonium, which is called a nitration process. This nitration process is followed by the nitration in which nitrite is used to is oxidized to nitrate by nitrite oxidizing bacteria. So in both process, if you see there are 25% oxygen is used to oxidize this nitrite and 75 oxygen is used to ammonia oxidize to nitrite. Similarly, in the second side, the right side, nitrate is converted to nitrite by heterotrophic bacteria followed by the denitration. In 2.0, which is called as the nitration, after ignoring the nitration and denitration part. So we have just the nitration and denitration, in which the same process is going on, the ammonia converted to nitrite, and which reduce the some part of the nitration and denitration, where in the previous slide, if you see there is 25 partition is used, there is 40% carbon is used. So that part is removed and we reduce the we reduce here that part and we get the advantage from this nitration 25 percentage reduction in oxygen demand and 40% reduction in carbon, 40% reduction in biomass too. After that, in 1999, the Anamox term and the reaction occurs in the SPR tank introduced by the Strauss et al. The partial nitration Anamox process involved in removing the nitrogen, also called the deammonification process, where we had received the advantages as mentioned here. We needed to control nitrate in the achieving the desired goal. So the controlation of nitrate is the for the Anamox optimal to getting the Anamox in the optimal form, which is 30 to 35 degrees Celsius, low SRT 1 to 2 days, and low dissolved oxygen. And we get this advantage 63% reduction in oxygen demand and 100% reduction in carbon demand and 80% reduction in biomass production. And no alkalinity, additional alkalinity is reused also. Let us see in the full scale installation. From the literature survey, it is found that 25% of full-scale industrial plant installed as compared to the municipal installation plant, which is in terms of very less, but it is growing day by day. The graph on the right side presents full-scale plant installation with respect to the year as well as the publication in the field of wastewater treatment plant that tells the installation is increasing per year slowly during the period of 1995 and 2003, and after that it's gradually increased day by day. So obviously there are so many challenges we have to face and we have to resolve in the later slide. So here we are just talking about the important challenges during the development. Some of the important challenges mentioned here, you can see here, which is divided into two parts. One is fair complexity and second is environment change. So depending on environmental condition, which tells the some environmental conditions seldom change, thus need to define long-term adaptation as the response to environmental condition that remain relatively constant throughout the lifetime of a species or organism. The non-linearity is very complex problem, so which is very initial to which is very important to solve it here. So like example, the aeration and no aeration, which is directly associated to the operational cost. So non-linear process is very tough to solve. Over time, inflow flow concentration continuous change. So untreated water, that is the influent inflow, is a continuous process. It doesn't matter a day or night. Need to treat this water by using optimum strategy, and control by manpower is not an easy task. So the control by the manpower is the factor is the operating aging. It is related to operating aging, which is a major factor, cause effect on the plant performance as well as the cost. So the goal of the water quality standard are to protect public health and the environment and to maintain a standard of water quality consistent with its designated uses. Water quality is determined by accessing three classes of attribute. One is biological, chemical, and the physical. The physical property of water quality include temperature and turbidity. Chemical characteristics involve parameters such as pH and dissolved oxygen. So let us discuss about the architecture which is posed to the Tucson Heavy Company. Here you can see the architecture. So here is the plant. So data is collected from the plant using SCADA system, which is called as Simon system, and it's connected through the PLC using the OPC client and OPC server. And we proposed here some smart and functionality known as the intelligent HMI modules like offline profile, risk assessment, decision control, and unit cost calculation are responsible for the normal operation of the wastewater. Besides these, we also provide the soft sensor here. So basically, the C Sharp is language is used for front-end coding, and the MATLAB tool is used for creating DLL, dynamic library linking of modules that reference into as a backend, and the historical profile is saved into database which is used for SQL Server. So MATLAB is used for the simulation the program. So here is the first module of a smart Anamox system, which is known as operation, data monitoring, and analysis. So you can see this is the GUI which is running on the plant in the company of Doosan. So the online profile display is presented here, which tells the real plant behavior. The Ethernet medium has used to connect the plant and GUI with the help of Open Access DLL, which is known as OPC to TLL. So here is some command which is used to connect the plant and the GUI interface. This is the another example where we can see the DO and the ammonium trends and observing in the concentration inside what's going on inside the SPR tank. Here is the generated CSV file by the SCADA can from the plant can be imported and saved to this database for future reference. Here we investigated the offline data, historical data, and compare their trend with the online profile. And we can observing what's the previously we get and what is going on nowadays. This is for the exporting the data in the future perspective if needed. So let us discuss about the smart simulator which is used to make the SPR model. So here in developing the virtual simulator, it is important to choose the correct model on the real plant condition. Since based on the challenges and the process complexity, we have choose mechanistic model due to its completely relates our plant behavior. So in the mechanistic model, the biological characteristics are not fully reflected. So we need to some, uh, yeah, but there is uh, reduce the complexity, process complexity, and some solution to reduce the challenges. So that's why we choose the mechanistic model. It is very mutable and easy to change in that model. So here the ordinary differential equation model we choose in the ASM, which is known as the activated sludge model. So as before selecting the model, it is essential to know about what's going inside the SPR tank. Thus, we need all reaction in terms of differential equation. This SPR model differential equation is solved by the OD MATLAB tools, and the parameter calibration is used. Some of the parameters are very sensitive, so this is very important to calibrate that parameters. So we use is the mean absolute error for that and determine the optimum influent nitrite and ammonium ratio, and then get the model for that parameter. And for that purpose we need to data because it's play a vital role in getting the exactly same behavior as real SPR tank have. So larger data is taken for the model calibration. So here I presented some from the literature. There is some ASM model which has the equations 12 dynamic state concentration variable and reference by the 11 biochemical process. which is used to make this model. But the problem is ASM model has the limitation and some problem. So basically it is difficult to actually identify the characteristics of the influent wastewater. So it doesn't take into account that the properties of organic materials such as biodegradable substrate change within a given ratio. The coefficient in the equation are assumed to be constant, which are not reflected in the model. So online application of control is not useful because it is difficult to update and estimate the parameters of changing model online. Difficulty in identifying some actual wastewater characteristics. Very specialized knowledge is required to understand all the model's internal mechanism. Lacking identifiability. Many parameters and state variables have been introduced to more accurately describe the nature of the process, most of which is not directly measurable. That means calibrating the model requires much effort and the reliability of the calibration result is also weak. Lacking verifiability, many state variables and parameters cannot be directly measured. Therefore, all parts of the models cannot be verified experimentally. Using expensive measuring equipment to calibrate and verify the model requires very complex and challenging experimental procedures. Species diversity doesn't change over time, which doesn't consider the effect of substrate concentration gradient, reactor characteristics, and sedimentation characteristics on sludge. And obviously problem due to nonlinearity because of its make the process complex. So these limitations, a model consisting of the factor that can actually be measured. So online identification is very important. In this model, we collected the system information and then we selected 38 parameters from the literature survey and which is based on the three uncertainty deviation which is described here 15%, 25%, and 50% because we need to auto tune that parameters. Here is the stepwise procedure performed. So firstly, we define the rule for the processing time, filling, anaerobic, aerobic, and drain, as you can see here. And then this table presents the identified highly sensitive parameters from the study where 32% parameter were reduced as compared to this study, that study, sorry. Algorithm Leavenworth-Marquardt is used to solve the curve fitting problems. In this case, the RMSE root mean square error is formula is used to calculate the curve fitting, how much it fit, how much it mapped the curve. So this table present here, which shows the 10 days data, different 10 days data, and their RMSE value, which which is used to validate the model accuracy. Here is the here is the another example of 1 day example where you can see the graph is have the real and predicted values and RMSE values. So their root mean square error is just 0.5, which shows the predicted value is very uh, is too much mapped, is completely matched. We can say that completely matched with the real plant data. And similarly in the ammonia and nitrate too. In the plant, is nitrate value is sometime is not good. So, but the model is present and work well. Is present some right graph here and right trend here also. You can see it. So yeah, here is proposed UI and their result and how much confidence level of that parameters, and these all parameters is selected we, and we see here the mapping of that and then their difference of in terms of RMSE percentage. So next is the soft sensor, which is most demanding nowadays due to sensor, because sensors are expensive and their maintenance too. So it is basically the demand of the company, many company, and nowadays is vast use of the soft sensor in the plant. Here, since biochemical and biological oxygen demand is a measurement of the amount of dissolved oxygen that is used by aerobic microorganisms and when decomposing organic matter in water. So on the left side, there is some online sensor where the ammonia and nitrate, nitrate and nitrite are expensive sensor, and this is the lab experimental offline data for testing. So the model accuracy is required based on the data quality and quantity. So the quantity is more and quality is good. So accuracy, model accuracy is good. So this is our problem. If you see here in this pie chart, the sensor and the control system has 16% cost. So it is very higher. So if you the plant use the soft sensor, so it's reduce the maintenance, but this is not included the maintenance cost, just the cost. So we can reduce the maintenance and the cost also. So this is very important. So for making a soft sensor, the experimental data has a small amount of data that elaborates less information and consume too much time in gathering large amount data. But it is very important and needed for the model accuracy and then get the simulation result. So here we are used three sensor: ammonia, nitrite and nitrate, and we propose the sensor with these three sensor, and the simulated ammonium concentration use the larger data set because of the sensor is some problem or something occurs or data is not best quality, so that's why we need more data, and then after that we get the good result. So we chosen many things to make a good model for the soft sensor. So we decided to check the data. So we check the data and reduce the raw set by using the PCA component analysis. So in the left here, describe the data with the largest variance, and this is describe the data with the next largest variance. So we are using here the artificial neural network for making this for developing the soft sensor. So the input is 7, which is including volume, TSS, total suspended solid, conductivity, ammonia, nitrite, nitrate, dissolved oxygen, something like that, etc. And then we effluent production is real plant data is ammonia, nitrate, and nitrite, and we predicted one output which is from the which is might be then ammonia, nitrate, and nitrite. So three sensors are there, and the one output based on this effluent production. So we data processing is side stream Anamox SPR process, online sensor and offline sensor. So we calibrate and check the result of both, and we find the hybrid model which is uh, good result and accurate result. We will see in the next slide. So here is one important thing. We define the rule to getting the highest accuracy of that model. So we define some thumb of rule, and we define the some pre-treatment of plant data. So before going to insight, so we remove some uh, unwanted zero or redundant data. We remove from that before entering the model, and then we get 85 to 95% uh, accuracy. So here you can see the result. Here four graphs mentioned regarding the ammonia and the nitrate. So and which tells the real data, which is black, and the pink is predicted data. So you can see how much it accurate and map. And this table present two things, RMSC and R square values. So the highest the RMSC value, then the model is most accurate, and the low and the percentage is 99%. You can see optimum. So the PCA Kalman NN, which is known as the hybrid soft sensor, is work great as compared to other models. So this is just check the which model combination is good. So we have four model combination. One is PCA Kalman NN neural networks, PCA neural network, Kalman neural network, and without neural network. So we find here the result says that the PCA Kalman NN is best amongst them. But we also validate by using the pH real and pH predicted value. So we check the model is how much accurate and how much it's mapped, and how the result is, we can say, is good. So so we found 70% model pH is mapped with the real data pH. So data is here, which is the plant data, and this is the fitting curve. uh, so pH data real and pH predicted here. So we found the most of data is mapped, which tells 70% of model is accurate. So we can say that okay, this model is right and predicted well. So this is GUI we presented, we proposed for making or creating the soft sensor in future. Beside this, we need to expert control and reduce the shoulder head of that operator and engineers. So here we provide some smart alarm and decision support based on the knowledge come based rule based control strategy. So here the chart logic is implemented for smart alarm and decision for operator if any cause error. So the cause is related to risk assessment and optimal control of monitoring. So this alarm is uh, case-wise logic here. So if something happened, so it generate prompt is prompted to the operator what he want to do, he need to do actually. So The case-wise control techniques to recover the system under the influence of shock loads. Inhibitory substances, their effects, mechanism, and control techniques are discussed. So this control logic is tested on the bench scale before implemented in the pilot scale. So the flow chart is actually here. So suppose if we see here the detail information, the pH if less than this value, that means the cause is acid base and industrial effluent, and we categorize two solution. One is normal and second is critical. So one stage is prompted, recirculation of tested, and then to the this term, and then if this is not work, then the second solution is prompted. So these are the detailed information of the prompt solution and some causes based on what's going on inside the SPR tank. So beside this, we provide some innovative and advanced decision-making control uh, for generating the processing, predicting the processing unit time, which is very important and time consuming by manually input in the prompt. So the main objective is to minimize the operational cost, which is directly associated with the unit working. So the consumption of electricity or consumption of energy based on this work. So we focus on the cost is very important. So this table is tell the rules. We assume that same in similar manner we in the previous slide. So and we define the time in 10 minutes for constant time for the model, and we subjected the some constraint values and some boundaries within this is very important. So here obviously some assumptions were made during the experiment. So processing unit time, which involves filling, mixing, aeration, settling, and drain, taken as rule. A complete cycle time, which is 10 to 30 minutes per sub-cycle. So one complete cycle is divided into sub-cycle. Volume size, which is 10% minimum or more filling. Set point is optimal set point for the for better ammonia for the better Anamox bacteria. During filling, the continuous mixing is processed and aeration always start immediately after mixing. So the reason is here why we define this assumption, because it is necessary for the model, and this is the flow chart of step-by-step flow chart for the model. So this is actually the a result from the model which provide the optimal schedule. As we can see here, the rule like that. So 1 and 2, 2. So this kind of occurrence is for making the unit times, and this occurrence in same number counted by and multiplied by 10, because we already mentioned constant value here. So we like this example, you can see one occurrence one time, so it's multiplied 10, which is relates to filling time. So filling time is 10 minutes, and same as the aeration or something and exit time we calculated here. And here we can see the table in which the aeration is previously before applying the proactive scheduling, so 420 total time, and after applying the proactive scheduling it is 380, so it is reduced the aeration time. So this pie chart, it shows that 63% of aeration energy reduced compared to the conventional biological nitrogen removal process. Here you can see in the traditionally 48% aeration was used. With this, we also check how much greenhouse gas emission. So we check 69% greenhouse gas emission is saved with this prediction. Let us see the uh, nitrogen removal rate on bench scale. So before applying the proactive scheduling, so the firstly is the starting in the starting 87% nitrogen removal rate achieved, and then this area it was decreased as 7%, and after 75 days it stabilized and then get the 75 around 75 or 74% nitrogen removal rate. But after applying the proactive scheduling as compared to before applying proactive scheduling, there is so much fluctuation. But in this, there is no or normal operation without having some more fluctuation, and we get the 80% nitrogen removal rate. We also validate the process that validate the proactive scheduling model. So we get the 1 day data of that plant, and we validate with the predicted data from the proactive scheduling model here. So this value is from the real plant data we input into the proactive scheduling model, and we get the say we get the good result in the next slide, like here. So before, the data has 54% nitrogen removal rate, but after applying the proactive scheduling, so we get the 83% removal rate from the model. This is the result of the model compared with the plant data. So this GUI and their result is mentioned here. So this is the optimal sequence from the sequence set. So the model generate two things. One is sequence set, and second is optimal sequence. Cost estimator. So the last module is we provide the cost estimator for the calculation of the operating cost. So we provide the operating cost expenditure here. The backend calculation of OPEX performed by using equation these 1 and 2. So this is very normal equation we use to calculate the cost of operating cost, and then we calculate the per year and per month, some like that. So the concluding remarks is PCA analysis establishes the correlation between easy to measure and hard to measure parameter. It assists to clear the close relationship between parameters and their effect, vice versa. Installation of sensor are associated with higher cost and that can be replaced by soft sensor, whereas no need to maintenance of this soft sensor. So we reduce the soft sensor cost here, providing the soft sensor. A mathematical model that acts exactly same. So we provide the SPR model, which is important to generate some data, and we can simulate our data to there. And plant data is not consistent, sometime due to many reasons. So SPR model might be fail to predict accurately sometime. So that's why we propose the auto tuning of the model parameter are mandatory to overcome this failure. And SCADA system control the wastewater treatment plant and reduce uncertain problems. It is ensured by providing rule-come knowledge-based alarm system to operator and engineers. So basically, this thing helps to the operators and prompting exactly solution for the causes occurs during the plant running. And besides this, we provide the innovative based mixed integer nonlinear methodology is incorporated with smart Anamox system and applied to bench scale for ensuring its correctness, which is known as the proactive scheduling model. And for plant processing and maintenance costs are estimated by SaaS cost estimator. Thank you very much. This the acknowledgement to the Young Ministry. This research was supported and funded by Young Ministry. Any question? Thank you very much.
Thank you, sir, for an amazing session. Your knowledge will surely impact young researchers and aspirants, and they will learn how you can collaborate the computer technologies with other fields like
Yes,
you did.
right.
So, if our participants and viewers want to contact you, they can contact you on your email ID. So, can you share your email with us?
Yeah, sure, sure. Uh, I will share by email or here directly.
So, you just tell me,
Okay. Alam.
indicate comment
Yeah.
section.
Okay. Okay. So this is actually my email. Have you got it?
Okay. Yes, sir. Thank you.
You're
It's
welcome.
alam, alam dot chem at the rate yu dot ac dot kr.
Yeah. Right.
So I'll post your email ID in the comment section also. So if
Okay.
anyone wants to contact you, can do it.
Yeah.
Thank you
Sure.
so much for your valuable time and sharing your knowledge with participants. Thank you
Yeah.
so much.
Thank you very much for inviting me this talk. Thanks a lot.
Now, the next distinguished to honor us with his presence is Dr. Heather Raza from University of Essex, United Kingdom. So, has done his BTech from Integral University, MTech in Computer Engineering from the Manav Rachna International University, and the PhD degree in Computer Science from University of Ulster, United Kingdom. So, has a diverse research interest in big data and analytics, brain computer interface, deep learning, transfer learning, non stationary learning, and domain adaptation. We also have a research interest in artificial intelligence and machine learning, EEG and MEG signal processing, AI in decision making for healthcare. So also have publications in reputed journals and currently working on different projects. So we'll also deliver a technical session on computer vision image processing and blockchain technology. Over to you, sir.
Okay, thank you very much. Thank you for the introduction. And good morning, everyone. I'm Heather Raza, as I've been introduced. And today's topic is brain computer interfacing. And I'm a lecturer in AI for decision making in the School of Computer Science and Electronics Engineering, University of Essex. And means you can visit me, you can visit my work at segiheather.com. And these are my Twitter and LinkedIn handle. So, let's start. What is brain computer interfacing? Brain computer interfacing is a communication system that do not depend upon the peripheral nerves and muscles. So, like as you can see over here in the image, that what we do in brain computer interfacing, that we put some kind of a EEG cap on our head, right? And we reread the brain signals from the human mind, and we translate them into a computer command. So the people, those who are suffering from different form of neurological disorders, such as having stroke or any kind of issue in their brain, so they can directly communicate with the computer and they can operate any task, they can do whatever they like. So let's take it much forward. So means because two definitions are very very important. So BCS system allow a paralyzed or logged in patient. So you have guys seen Stephen Hawkins and any other guys who got stroke, which is called paralysis in India. So the patient, those people who are suffering from this, they can communicate using writing words and simply passing computer commands, simply passing commands through a computer interface that recognize the EEG from the brain, and we translate those signals into computer commands with the help of specialized algorithms which we design. And this approach is called non-oppressive, non-invasive approach. And here we use brain electricity from the brain, which is EEG, and magnetic field which produced around the brain, which is called MEG. So there are two techniques, EEG and MEG, by which you can record the brain activity. So I worked on both, and I'll take you forward. So this is one of the scenario. You can see that here, this experiment and this work we did with IIT Kanpur when I was in University of Ulster, when I was doing my PhD and postdoc. So I will explain you what is this. So can you see a person? This guy is suffering some form of stroke, so he can't able to move his left hand. So what we did, we partnered with IIT Kanpur is one of the reason is that we have collaborated with IIT Kanpur because they are good in mechatronics. They are pretty good. So they have designed this particular part of exoskeleton. You can see the hand, artificial hand, and we have designed this means not this cap, but the algorithm behind this. So what we did, we designed a kind of a brain-computer interfacing system where when a person who are suffering from a stroke and means it is said in neuroscience that if someone is suffering from stroke and they perform some kind of a mental imagery or a physical imagery together. So for example, physical activity, I'm moving this hand right this, and if I'm imagining the same thing in my mind that I am trying to attempt my move my hand, some kind of activity will generate in your brain, and that can regenerate your neuroplasticity in the brain. So this was the hypothesis that when somebody is going to imagine that they are moving their left hand, and we will detect on the computer this exact exoskeleton which is on the hand will help that paralyzed patient to do a physical exercise like moving his hand like this, right? So we did this study for nearly maybe like this project went for nearly 2 years, but with the participants we spent like maybe 3 to 4 months. And within this experiments, we found that yes, our hypothesis is good. Previously, the hypothesis was that only mental imagery was sufficient. But if we do mental imagery, like yes, imagining in your mind, but if somebody is able to assist you, for example, a physiotherapist came and they help you to do the hand movements like this, right, when they come to your home, But suppose they're in the pandemic or any situation where nobody can come to your house or you are alone, how can you do the exercise? So this artificial hand called exoskeleton will able to help you to do your exercise, and you can do wherever you like. So this system we designed, and it was a good study. And this is my BCI team in Essex, where I'm currently. So this is my team, and we all work together. So we have a quite a diverse team over there, and these are two heads, Professor Ricardo Poli and Renal Scherer. And this is our team, and there are a few people from India as well, and from Europe, America. So we have a quite a diverse team over there. We all work together on several projects. So let me take you to the protocol of translating thoughts into command. So what we do, why this EEG and brain computer interfacing system was there. So brain, brain is a full of neurons, and these neurons are connected to each other by axon and dendrites. And so, for example, I'm just giving you a scenario. I'm not reading the slides because that's what you can read. So consider a scenario that when you touches a hot glass or maybe any kind of a hot material, right? How you quickly remove your hand, or whatever thing we do, we our brain sense it very fast. How? Because in the brain the neurons are connected to each other, right? And when the neurons are connected to each other, one neuron passes information to another neuron, and when these neurons work together, what they do, they form a very big highway kind of thing. The speed of neurons on which they work is pretty high, right? So it's pretty impressive. So when this neurons transfer information from one neuron to another neuron, and they do it through transferring some kind of chemicals, right? And when this chemical passes from one neuron to another neuron, some kind of a micro, or you can say a micro or a nano voltage generate in the brain which we can't feel. And what these electrodes, what we when we put these electrodes on the head, we read those electrical activity from the brain, and that we call EEG, right? So we read those activity from the brain, from the specific part of the brain, and then we design computer algorithms to translate those electrical signals into a computer command. So for example, if I tell you that, for example, if I'm moving my right hand like this, right? So because this part of the brain on your left hand side, means from center to the left over here, this part is responsible for right part of my hand, right? And if I do my left hand, this part of the brain is responsible for this, right? So when I do this, some kind of activity is happening. So these electrodes are going to read that information from your brain, and then those are very minute, very noisy data. And when this data will come to us, when we record, we clean that data. We do a lot of work on that data, and then finally we can detect that if someone is imagining left hand or right hand or whatever they are do. So this is how we do machine learning and AI into brain computer interfacing. Now, some major historical events in BCI. So this all started in 1924 by Hansberg, a German neurologist, uh, who was the first person to record the human brain activity by the mean of EG. After nearly more than 40 years, the research finally began in BCI to design a system that began in the University of California, Los Angeles, UCLA. 8 years later, a prototype was implanted into a man blinded in the adulthood, and the experiments were performed, and first neuroprosthesis device was implanted within the human mind, right? And in 2005, Matthew Nagel was one of the first person who uses BCI to restore the functionality due to the paralysis. So, so there is a guy. Means, for example, they're suffering from paralysis. So Matthew Nagel was the first person who used BCI to restore his full means functionality of moving their hand or leg, whatever they are having the stroke. So yes, that study was very successful. And in 2013, Duke University researchers, what they did, they took two rights. One rat is from this side, and two rat is from this side, and they planted some kind of a neural chip in their brain, and one rat can communicate to another rat with the help of BCI by transferring one message from one brain to another brain and this brain to this brain. So this is how it's done. And later, the motivation why this system is being designed, because BCI is designed to give a disabled people a way of communication to operate the processes, like for example any kind of device they want to do. Like for example, if someone having a stroke in their hand, they can get an artificial hand or maybe a kind of a robotic glove by which they can hold something, by which they can drink, so they can operate to their daily life. They can operate their wheelchair by the brain signals. And the targeted people, those who have a neurological some kind of a disorder, are mainly ALS, cervical spinal injuries, stroke paralysis, cerebral palsy, and ampute. So these type of diseases, mainly when occurred in the brain, the BCI is quite useful for them. Now, let me tell you how it's done. So, can you see the human brain? And in the human brain, we have several layers over there, right? It means first we have a skin, then we have bone, then the brain will come. So, different things are there, right? And we can record EG from up. We do not need to operate the human brain to put any kind of say like electrode inside the brain. So when we do not operate, we just put the cap, we record EG. But when we put an electrode inside the brain, we record ECOG. But when we put a chip inside the brain by doing a surgery, we get a very best signal, but that is not very useful. So when we get this type of a data, what we do as a machine learning and data scientist, we process that signal, right? We clean the data, we reduce the dimensionality, we find the good feature in the data, and then we control the devices. So when we control the devices, what we do, first we have to like teach a BCI machine that this is how your brain signals look like. So in machine learning, we have two parts: training a machine learning model and then testing a machine learning model. So what we do, first we get the data from the human brain, we ask them to do left hand imagination, right hand imagination, foot movement, tongue movement, and when we record this data, we give this data to a machine learning model to learn that how my brain data looks like. And then when my computer algorithm is ready, my machine learning model is ready, we put that into a system, in a BCI system, and then we go say person to go into a real world situation and then control the devices by itself. So for example, you can write a message on the keyboard, you can take a phone, like type a text message, you can switch on switch off lights, you can switch on your television, you can operate your home appliances, right? Lot can be done. So this is a way of environmental control, this is a way of communication. You can control exoskeleton with what we did, right? You can control your wheelchair, right? And the same thing can be used for rehabilitation as well. So in the steps, as I've already told, but this is a more detailed picture. So for example, when we get the neural signals, we do the signal acquisition, right? When we get the signals, we do feature extraction, we train the machine learning algorithm, and then we control these devices, right? And you can see that a feedback is also given to the user. So for example, when I was training the machine, when I was telling my machine that this is my data, right? So what is happening when I'm doing a task? So for example, you are playing a pinball game on the computer with the help of your mind, right? A ball is dropping and you are trying to control the plate with your mind. So for example, if I'm imagining my left hand is associated with the left hand side of the pinball plate, so if I'm catching it properly when I'm training a machine, and if it's done perfectly, a happy message will be sent to a user, maybe a kind of smiley or something, by which user can learn that yes, he's doing that a right way. So for example, if I'm doing it, I'm just imagining that I'm doing left and it's not moving cursor, then I have to think in some another way that I'm not thinking it properly, right? So you have to adjust your brain accordingly. And what I personally found in this study, that the person who do meditation, those who do mindfulness, right, they are a good BCI user because they know how to focus or how to switch your brain into one mode to another mode. So you should learn how to control your mind, right? So this is very important. Now there are several type of BCI. So there are invasive BCI, partial invasive BCI, and a non-invasive BCI. So I didn't work in invasive and partial invasive. I mainly worked on non-invasive, where no surgery is involved. You can directly put the electrodes on the head. So if we put electrode on the head, then EEG. If we put a person into a MEG area, I will tell you what is that, then we record MEG. fMRI is different type of brain data as well. And in invasive, what we do, we have to do a kind of a neurosurgery to put a chip inside the human brain. And when it's a partial invasive, what we do, I told you that we put an electrode not deep inside the brain, but just opening the scalp and putting the electrode, because with the scalp, the quality of the data which we get is not that great. So as I told you, when we record the data from the top of the brain, we got EEG. And when we put the electrode deep after, like just after the scalp and the skin, right, what will happen? We got ECOG. And when we put a chip inside the brain, like a kind of a chip with pins, a kind of a circuit designed over there, then it's we get a raw data. And this is the best one, but this is not feasible for everyone. This is not also feasible for everyone, but this is feasible because you don't need any surgery. So this is how it's look like. Non-invasives look like this, and invasives look like this, that we put like chip inside the human brain. And yes, so I told you that I worked on both EEG and MEG. So when we work on EEG, as I told you, we put a kind of electrode on the human brain, and we put a reference electrode just to clear up the signals. So what we do, we get the data, and data will look like this. So if I zoom it, you can see the data will look like this, right? Now, when we do MEG, we do not put any kind of a sensor or any kind of electrode on human brain. What we do, there is a specific kind of a big device, like a MRI kind of a device, where a human brain need to be placed over there. So there is a specific seat. You go and you just sit like there. And what we do, when this electrical activity is being generated, and electrical activities from the brain is generating from everywhere, so this electrical field will also produce some kind of a magnetic field. So in the brain, we record this magnetic field, and again we can design a system with the help of MEG, and that we already did and proved. And this is an introduction to EEG. That EEG is called electroencephalogram, and the scalp recording comes from the scalp, and it's kind of a waveform, and the data is in microvolt, which is pretty small. There you can record in many ways. You can record in bipolar mode, you can record in referential mode. It's up to you how do you want to record the data, because you have to play with your signals. And this is the setup it's look like. And if you go for MEG, as I told you, MEG device is pretty big, which looks like this, which is not portable as well. So human need to go there and sit, and then then it can be recorded. And the technology behind the MEG is called SQUID, which is a superconducting quantum interfaces devices, which is being placed over here, and that will record your data. So magnetic field being produced, and we record that data. And the recording unit is femtotesla or picotesla. It's up to the device in which form they want to record the data. And the only drawback with MEG is that it is very, very, very expensive. Within the UK, we have only 13 to 14 MEG machines. And in India, I know in Gurgaon, there is one research center where their MEG machine is there. So I think in India, there are only 1 and 2 MEG machines are available. And we have worked on the system, and we have designed a BCI for it. So now going to the next part, because we have very less time and I have a lot things to present to you. And there are several advantages and disadvantages in EEG and MEG. So you can see the temporal resolution of the EEG and MEG is nearly the same, but the spatial resolution of EEG is pretty big than the MEG machine. And these are other different type of data which you get from the brain, fMRI, CT, MRI. So but these are not for BCI. For designing a BCI we can only use MEG or EEG, because here in these two type of the means in this two type of system we get the data as a time series signal. So that's why it is very important. One second. Yeah. So in EG and MEG comparison, the signal magnitude here is 10 microvolt. Here is 10 femtotesla. Measurements are secondary currents. Here it's primary currents, right? And the signal purity, it's being distorted by the skull and cap. In the MEG, it's little affected because you are recording the magnetic fields. Temporal resolution of both are nearly same, but the spatial resolution here it's less than his in nearly 1 centimeter, and in MEG machine it's very dense, so it's pretty less. So you can record the brain in much detailed way. And experiment flexibility moves with subject. So if we go and use EG, I can move my head like this if I'm doing something. But in the MEG, you have to sit and being static. You can't move your head because that will create a noise in the data. And dipole orientation, it's tangential and radial, and here tangentials are better. So let me show you the different type of BCI paradigms. So here you can see on the left hand side, we can use our eye to write a message on the brain, which is known as P300 modality of the brain, modality of the BCI system. SSVP is again a kind of controlling the system with the help of eye. And SMR, which I will tell you later, we can imagine the moment and control that device. So I'll take you through each of them because they are very important. So in P300 you can see what is happening. P300 is a paradigm where the user is requested to focus on something. So for example, on the screen there are several letters are written, right? And those letter have a specific orientation, and what will happen in that particular means screen, that each letter is being sparkled with a light. A flashlight will pass through, and for example, if I want to write a message, maybe my name Heather, then if I am watching at H, and when the light on H will appear, what will happen? A certain kind of activity in my brain will occur, and our computer algorithm will read this type of activity which is here, which is, you can see a drop in a voltage. That means the person is looking at this letter, so the message will be typed. So if I want to show you a little video of P300, so P300 is this. So this is a BCA. So see what is happening is this type of light is appearing, right? So it's flashing, and when I'm specifically focusing, so for example, this person is going to write vision, I believe. So he's particularly focusing on V. See, the V is written. Now he's focusing on I, and when the light on I will come, the signal will be read from the brain, and the message I will be written. And nearly he will complete the whole experiment, and at the end he will write vision, right? So this is how the P300 systems work. SSVP, in SSVP the things are nearly same, but instead of focusing on a specific word, what will happen? Uh, so what will happen basically? The screen will flicker in different frequencies. So, for example, the left hand side of this particular block will flicker at the frequency of 10 hertz. This part will flicker at the rate of 20 hertz. This is 30 hertz, and this is 40 hertz. So, if I focus on particular frequency, maybe 10 hertz, then what will happen? My brain will match the corresponding frequency, and I will select that thing. So, uh, let me show you again a quick video on this. So see, so this guy is trying to control this robotic arm with SSVP. So he's focusing now at 2 because all the circles are flashing or flickering at different frequency. So now he's looking at 4, so all the 4 fingers are open now. Now he's looking at 3, the third finger will close. Now he's looking at 2, the second finger will close. Now he's looking at 1, right? So all the fingers are open now. So this is how this SSVP system works. And I worked on this brain computer interfacing based motor imagery where you can see what happens. That, for example, if a lady who is there in a cartoon, she is skiing, and when skiing, because she is doing a motor task, that motor task means she is doing something physically. So what will happen? A red spot in the brain is coming. That means some type of electrical activity is generating from the brain, right? But for example, she got stroke, she can't do. But if she is sitting and just imagining in her mind that she is skiing, so for example, if you are sitting, you won't able to do, but you imagine that you are doing this, right? The activity of the same activity, but not with that power, but activity will generate in your brain, right? Some kind of activity will generate in your brain, and we read those activities to detect if someone is just imagining, because stroke patient can't do anything, right? So they just imagine, and we read these imagination, and we convert these imaginations into a control commands. So what we do basically, you can see for the left hand side and the right hand side, uh, this type of pattern will generate in the brain, and we read the signals. And if you see, C3 is the left part of the brain, C4 is the right part of the electrode, and these two difference we measure. So this so if I'm zooming it, so C3, so this part of the like curve is coming from the right part of the brain, this curve is coming from the left part of the brain. So what computer will learn? The computer will learn the gap between the two, so they can draw a line. So if anything's come here from this electrode, it's left, and if this is coming from here, so it is coming as right. So this is how we train our algorithms, and it is not that easy, believe me, because we have to do a lot of signal processing and machine learning to generate this gap, because in raw signals you can't see this gap. So this gap only comes after lot of signal processing, right? And there are several challenges in the data, that the data is quite noisy when you get from BCI and EEG. It's suffering from outliers. They are very high dimensional. The demand is that we need a BCI machine where we don't have to train. So training, like for example, if I am going to use it, I have to first teach it that these are my signals. So I want them not to teach, or maybe to teach on very small data, because it's consumed time. So we have to get rid of this as well. And non-stationarity, so for example, the human brain is changing ever time. So for example, if I am doing my BCI recording in the morning, and if I do my BCI recording in the evening, my signals itself change because of my mood, because of my tiredness, or different reasons. So these are some challenges if you want to work forward, right? That's, yeah, so means these are some open area where you can work. And as I have told you, these are some challenges which I have written. And thank you for your attendance. And these are my collaborators, and these are my funding bodies. Yeah, thank you.
So much, sir. That was really an extraordinary session. Thank you, sir, for showing your keen
Thank
interest
you.
in
Thank you. Thank you.
knowledge with our participants. It will surely help everyone to understand this topic better. Thank you once again.
Thank you, ma'am. Thank you.
We will be having our last technical session starting at 11:30 a.m. by renowned speaker Professor Dharmen Singh from IIT Roorkee, followed by the valedictory session of RAICT. Link for the next session is available in the chat section, and I request the viewers to patiently stay connected with positive spirit. Meanwhile, we are having author oral presentations sessions running along on the Google Meet platform. Thank you. I sign off for now.